Hello guys, welcome to another interesting session of our DSA course and you're watching my project ideas. So this is gonna be the last lecture for the first chapter and we are gonna learn about space complexity. So stay tuned, brace yourselves and let's move forward. Here we are. What is space complexity? Space complexity of an algorithm is basically the total space taken concerning the input size. So no brainer, what is space complexity? As time complexity stands for time, space complexity stands for space. It is taken by the algorithm concerning the input size. Space complexity includes both your auxiliary space and the space used by the input. So what is the space used by input? Depends on your input size. What is auxiliary space? It's a temporary space that can be used by the algorithm, like the recursive call stacks, those spaces also. Let's take an example. If we want to compare standard sorting algorithms based on space. Okay, so we are going to compare the sorting algorithms here, which is based on space. So the auxiliary space will be a better criteria than the space complexity. So merge sort, what is auxiliary space? It is basically the temporary space used by the algorithm. So the merge sort uses big O of n auxiliary space. Insertion sort and heap sort uses big O of 1 auxiliary space. So the space complexity of all the sorting algorithms is big O of n. Because we are taking into counter of the auxiliary space here. Space complexity goes hand in hand with the time complexity. Again, it can be measured using big O. If you are going to create a size n array, an array of size n, it will require big O of n space because n different sections are required. Each number will take some certain amount of space. If you create a 2D array, so that will be n into n, simple because it's a two-dimensional array. So it will take big O of n square auxiliary space. When you're in the recursive call stack, like when we studied about recursion, see, the function is taking a parameter and it is decreasing by n minus 1. So a recursive call stack, the space also matters and the space also counts. You know the time complexity is counted as well as the space also comes into count. Okay. So what is a stack? We will be learning in the upcoming lectures. So stay tuned. Be with me here. Whatever I am telling you, just keep in mind of that. And again, if you have any doubts, if you have anything to you want me to cover up, then please write it down in the comment section. Then, how does each call stacks add? See, add 4 because here you have a recursive call stack and it is add n minus 1. So each parameter is decreased by 1 here. So here, when you're writing add 4, then 4 minus 1 is add 3. The next iteration add 2, next iteration add 1, then add 0. So each of these calls will be added to the call stack and takes up actual memory. So it is big of n space. However, just because you have n calls, total does not mean it takes big of n space. So if you have n calls, it does not mean that it will take big of n space. No, it doesn't mean like that. Look at the function here. You have an add sequence function right here where your parameter is int10. So int sum is equal to 0 and you're taking this loop into counter. Int I is equal to 0, I is less than n I plus plus. Then sum is equal to sum plus pair sum I and I plus 1. Then you have to return sum. Again, you have a pair sum x and y you take into counter and you return x plus y. So this is basically pair sum function where you are passing the parameter I and I plus 1 and here you are passing the parameter x and y. This loop runs for n times and this is a pair sum function where the sum happens. Okay. So how many calls will be required here? N number of calls because this loop runs for n times. So this function will be called n times. And those calls do not exist simultaneously on the call stack because see, after one call, you're going to the next call. So in one call stack, at a single time, only one time the function will be executed. Okay. Then what is a note part here? So it's necessary to mention that space complexity depends on a variety of things such as the programming language you're going to use, the compiler which you're working on, or even the machine learning, the algorithm. So the machine which is running the algorithm, the machine on which you're working on, the compiler, and the language which you use, all those three matched, combined together, and they provide you the space complexity. So coming to this program right here, see, you know that this loop runs for n times and this function is called for n times. So you can say that, yeah, big O of n space is required. Okay, no problem. But at a single instant, only one time the loop is running. So you're going to call this function only for once. So here, this thing is written here that at a single instant, you need big O of one space. In the next call, this space will be used by another variable. Again, in the next call, that space will be used by another variable. So that space will be overwritten. That's why we are using, or we have big O of one space. So with this, we complete our first chapter. Kudos to all of you. Thank you for being with me. And we completed the first chapter, that is the analysis of algorithms is completed. In the next chapter, we'll be learning about the mathematics, which is going to be a lot more interesting. And we are not going to have much more theory part. You will be diving towards the coding section from now on.